I had a question about application exercise 4-2. It seems like a million years ago since we were here, but it's part of the material that you are responsible for exam 3. Anyway, let's walk ourselves through this, and it'll be a good chance to review some of the basics of pollution control. All right, so two firms can control uniformly mixed emissions at the following marginal costs. Marginal cost firm 1 is 50 times the amount of cleanup that firm 1 does. Marginal cost for firm 2 is 25 times the amount of cleanup that firm 2 does. So rising marginal costs, rapidly rising marginal costs. All right, assume that with no control at all, each firm would be emitting 20 units of emissions, or a total of 41 units for both firms. What per unit charge should be imposed to clean up 21 units in the cost-effectively? It should read in the cost-effective manner, or just clean up 21 units cost-effectively. All right, report with a number writ large in Sharpie ink on a half sheet of paper. Let's get to this. The framework that you want to use is this one from Chapter 14, Figure 14.3. And notice what we've got here. We've got a framework where left to right we're counting the cleanup by firm 1, and right to left we're counting the cleanup by firm 2. Really, we should have another set of axes here. Marginal costs for firm 1 are going to be a ray from the origin. Actually, in our case, it's going to be quite a steep ray. Marginal cost of firm 2, a flatter ray, and our graph would be scaled 0 to 21. But anyway, notice that the efficient outcome is where marginal costs are equal. That's something that we've seen before. But also notice that an emissions charge equal, or even probably a shade higher than the marginal cost at that optimum level, that's going to bring about the desired level of cleanup, and also it's going to allocate cleanup to the firm that can do it more cheaply. Because the logic of an emissions charge is if there's an emissions charge of size T, I'll clean up if it's cheaper to clean up than to pay the emissions fee. But after, if cleaning up is more expensive than that fee, I'll pay the fee. So you end up, firm 1 will clean up all these. Firm 2 will clean up their first, in this case, their first 5. One second. Remember our framework, we're looking for the emissions charge that corresponds to that marginal cost level where the distribution of cleanup responsibility is optimal. Okay, so we have our frameworks down, and now let's solve the problem. We know that from the equimarginal principle, we know that that's supposed to be an M. Marginal costs of firm 1 need to equal marginal costs of firm 2. And remember that the marginal costs of firm 1 were 50 times the quantity of cleanup that firm 1 does, and that has to equal 25 times Q2. That's the marginal cost function for firm 2, 25 times the level of cleanup there. We know then that we'll divide both sides by 25, and we get Q2 is equal to 2 times Q1. Well, what else do we know? There's an infinite set of pairs of values of Q1 and Q2 that will meet that expression. Remember also that Q1 plus Q2 is equal to 21. They were emitting 40, and they now pollution output is capped at 19. They have to clean up 21 units to get there. Well, we can substitute 2Q1 for Q2. So Q1 plus 2 Q1 is equal to 21. That's 3 times Q1. So Q1 is equal to 7. And that means Q2 is equal to 14. Now the question asks what per unit charge. And remember our framework. I'm going to just back up a moment. So what we're looking for then is the marginal cost for firm 1 or firm 2. They should be equal. So 50 times Q1 is 50 times 7. That's 350. So MC1 is equal to 350. So a pollution, a permit charge or a emissions fee of 350, you could even say 351 would bring about the optimum cleanup. Any ton of cleanup that would cost less than 351 will get cleaned up, and any cleanup that was more expensive than that would not get cleaned up. So the per unit charge that would get us to 21 units of cleanup allocated efficiently between the two firms, that would be 351.